Good evening and welcome to lecture 8 of ME78 Thermodynamics course by NPTEL. Today we will be revising the topics of pure substance and steam power cycle and some questions from week 7 revision also. If time permits, we will be discussing. So to start with, some very basic concepts. So these were the questions that were solved in last week's tutorial session. So based on that, some revision of theory we will be doing. So to start with, first the concept of latent heat. So there are different types of latent heat is there. Latent heat of ice is there, of vaporization is there. So latent heat of ice means total amount of heat added during conversion of for ice to water at 0 degrees centigrade. Now, vaporization, latent heat of vaporization means the amount of heat, again, amount of heat added for water to steam at 100 degrees centigrade. That means what? Like latent heat of ice means you will be adding heat, but there won't be a temperature change for the ice at 0 degree. Instead, that ice at 0 degree will be turning into water at 0 degree centigrade. So that is latent heat of ice. Then latent heat of vaporization is the amount of heat that is being added to convert this water at 100 degree centigrade to steam at 100 degree centigrade. Okay. So from it is kind of like water from boiling point to dry saturated stage is called latent heat of vaporization or enthalpy of vaporization of latent heat of steam. Okay. Now, pure substance we have already discussed in the previous class. So, pure substance. Substance which is having fixed chemical composition. Then we have got saturation temperature and pressure. Temperature and pressure. Okay. Saturation temperature and pressure means if at a given pressure, the temperature at which liquid boils is called saturation temperature. Saturation temperature means liquid boils at a given pressure. Okay, temperature at which liquid boils at a given pressure. Then saturation pressure means the pressure at which liquid boils at a given temperature. Okay. Next is boiling point and melting point. It's the phase change that is happening from liquid to vapor is called boiling point. And a melting point is from solid to liquid whenever there is a phase change or the temperature at which solid starts to change its state from solid to liquid. Then superheated steam. So what is superheated steam? Superheated steam means dry steam If you for by heating further, um, or that process is called superheating. Okay, superheating uh, will will turn into superheated steam. Okay. Now, next up, sensible heat of water. So, sensible heat is exact opposite of latent heat. Sensible heat of water means the amount of heat required to raise the temperature of unit mass of water from 0 degree centigrade to saturation temperature. Okay. It is usually denoted by HF. Now, superheat enthalpy. Uh, that is heat supplied to dry steam at saturation temperature. Okay. To convert it into superheated steam at some temperature, at temperature T, is called superheat enthalpy. Now, wet and dry steam. So, wet steam means, okay. So, wet steam means the heat which partially evaporate um, and having water particle suspension is called, okay, steam, which has moisture content in it. Now, dry steam means uh, which does not have moisture content. Now, phase rule of pure substance. So, phase rule of pure substance means number of independent variable associated with multi-components, multi-phase system is given by the phase rule. Okay, it's also called Gibbs phase rule. So, it is given by n equal to c minus 2. Okay, so if So n is the number of independent variable. Then this is number of components. So if C is the number of components, then N is the number of independent variables that is associated with these components or phases. Okay. Number of components or number of phase present in equilibrium is given by C. Now dryness fraction. Dryness fraction means that is given by mass of dry steam divided by mass of total mixture. So if it is wet steam, or if the steam has got some moisture content in it, what will happen is mass of total mix will have the weight of water content and the dry steam weight. Okay, so if dryness fraction equal to 1, that means doesn't have any wet, or I mean it is not a wet steam, it is like it doesn't have any moisture. But if dryness fraction is less than 1, that means it has got more moisture content in it. Okay. So the opposite of which is wetness fraction. It is 1 minus dryness fraction you can take. Then explain the term degree of superheat or degree of subcooling. So degree of superheat. Degree of superheat means difference between superheated temperature, superheated temperature minus saturated temperature. Then degree of subcooling is like the extent or the amount by which water is cooled beyond saturated temperature. Okay. Um, so less than saturated temperature. If water is cooled, then that is called the degree of subcooling. Okay. Now Carnot vapor cycle. Okay. Carnot vapor cycle. So this is pressure P and temperature, sorry, volume V. So Carnot vapor cycle will be like, there are two isotherms. Okay. So this is one isotherm, this is another isotherm. If I take these two isotherms, one at T1 and one at T2, T1 greater than T2, then process 1 will be somewhere here, and then that will be going to process, wait 1 second, process 2, then that will be coming through process, so 1 second. Okay, process 3 will be along this isotherm, and process 4 will be like this, and it will go back to process 1. Okay, and this is 3, this is 4. So 1 to 2, then 3 to 4 it will be coming. So heat is added at 2 to 3. Q is added, then Q is removed, then these two are adiabatic processes. Okay, so this is how Carnot vapor cycle is there. Now, triple point. Triple point is the state at where all three phases coexist in equilibrium. Then critical point. Critical point means the highest pressure and temperature at which liquid and vapor phases coexist. Liquid and vapor phases coexist in equilibrium. Now, okay, another equation to calculate entropy change from saturated water to superheated steam condition. Steam. You can use entropy of superheated steam equal to entropy of gas plus CPS or log T superheated by T saturated. Okay, so SG is dry steam entropy. CP is specific heat of superheated steam. T, this is superheated steam temperature, and the other one is saturation temperature. So that's about it. Okay, now efficiency ratio. Efficiency ratio equals to actual cycle efficiency by ideal Rankine efficiency. Now, isentropic efficiencies are calculated using, isentropic efficiency for expansion It is actual work done by isentropic work done. So that is eta. Then for compression, it is the other way around. Isentropic work by actual work. Uh, Next is one second. Work ratio. Work ratio equal to net work transfer to positive work transfer. So work ratios affect the actual cycle efficiency comparing two cycles with same ideal efficiency. So the cycle having smaller work ratio would have smaller actual efficiency. Okay, higher work ratio means this SSC is lower, resulting in smaller size plan for the given output. Now, next is effects of condenser pressure on Rankine cycle. So, if you lower condenser pressure, so condenser CR pressure, then cycle efficiency will increase. Um, but the main disadvantage is lowering the back pressure increases wetness of stream. So that is like isentropic comparison of a very wet vapor is very difficult. Now, vapor cycles difference with gas power cycle. Vapor cycle over gas power cycle. So that is like one is vapor cycle. Vapor cycle has like isothermal heat transfer is possible. Heat transfer is possible. Another advantage is work ratio is high. Work ratio is high. Then why Carnot cycle cannot be realized in practical vapor power cycle? So main difficulty in attaining the Carnot cycle in real world is that isothermal condensation is stopped before it reaches to saturated liquid condition. So therefore compressor has to deal with a non-homogeneous mixture of water and steam, uh, because the larger specific volume of liquid vapor mixture before compression, um, and work input have to be very large. So higher power requirement is what is reducing the plant efficiency as well as work ratio. Okay, then uh, so then there are some terms which are related to power cycles. Uh, One is reheating. Okay, so reheating means um, the working fluid is heated in a device called reheater, and then it is again circulated in the plant. So what is the disadvantage of reheating is that uh, the cost of plant increases, and it increases the condenser capacity due to increased dryness fraction. Then advantages are like marginal increase will be there in thermal efficiency, and it increases work done per kilogram of steam, which results in reduced size of boiler and other related auxiliary devices for the same output. Then it prevents turbine from erosion. So these are the advantages of reheat cycle. Then there is something called feed water heaters. So feed water heater is used to increase the temperature of feed water to saturation temperature, corresponding to the boiler pressure before it enters to the boiler. Then there is something called bleeding. So bleeding, it increases thermodynamic efficiency as the heat of the blood steam is not lost in condenser but is utilized in feed heating. So by bleeding, the volume flow at low pressure is considered to be reducing, and this reduces the design difficulties of blades, and also container size is reduced. So reheating is supporting the boiler. Then feed water heaters increase the temperature of the feed water uh, before it reaches boiler. And then we have got bleeding, which is to help in reducing the condenser size. Now what is binary vapor cycle? So if it has got uh, a vapor that is exiting the turbine, is condensed by cold radiators and or cold water or any cooling fluid, and then cycle back into heat exchanger. Then this binary vapor cycle has got a combination of two cycles, one in high temperature region and another in low temperature region. So binary vapor cycle. Okay, so that's about it. Then the questions were based on ideal gas and real gas thermodynamic relations. So if you want, we can um, discuss those equations also. Okay, I guess I'll start with uh, one by one, like theory. So, ideal and real gas. Uh, yes, thermodynamic relations. So, when we talk about ideal gas thermodynamic relations, we have to talk about Charles' law. So Charles' law is V is proportional to T. So volume of a given mass of a gas varies directly as its absolute temperature. Uh, Given pressure is constant. Then we have got Joule's law. Joule's law states that internal energy of a given quantity of gas depends only on the temperature. Internal energy depends on temperature. Then there is something called Reynolds law. That means Cp and Cv of a gas remains constant. Then there is something called Dalton's law of partial pressure. That means total pressure of a mix of gas is equal to sum of the partial pressure exerted by individual gases. So if P is the total pressure, then P1, P2 are the individual are the partial pressures of individual gases. So you can just sum it up like Pn. Okay, that is Dalton's law of partial pressure. So this is total pressure of mixture of gas, and these are um, so this is sum of partial pressures of individual gases. So what is Van der Waals equation and how it differs from ideal gas equation of states? So Van der Waals equation includes the effect of intermolecular attractive study and shape factor when it comes to volume correction. Okay, so volume term and pressure terms are corrected. Um, with the pressure term, it will be having this intermolecular attraction of attraction forces will be there as the correction term, and volume it is having shape factor corrections. Then Maxwell's relation equations. We'll just write it down one by one. So one is P by V at constant entropy equal to minus P by S at constant volume. Then T by P at constant entropy equal to V by S at constant pressure. Then P by T at constant volume equal to S by V at constant te temperature. Then V by T at constant pressure equal to S by P at constant temperature. Now, Joule-Thomson coefficient. So that is equal to, so it is given by this equation mu equal to T by P. So it is defined as the temperature, change in temperature with change in pressure, keeping enthalpy constant. Okay. So that it is kind of like T proportional to P, and then T by P will give you a constant. So this will give you a measure of intermolecular interaction and then liquefaction of gases, etc. Okay, intermolecular interactions is what is causing liquefaction of gases. So that can be that sense can be made from this Joule-Thomson coefficient. Then compressibility factor Z. Uh, so compressibility factor, uh, it gives an idea whether a gas is real or ideal. So if compressibility factor is equal to 1, then it is ideal. If not, it is real gas. Then we have something called Clapeyron equation. So Clapeyron equation, it is a relationship between saturation pressure and saturation temperature, and enthalpy of evaporation and specific volume of two phases involved. So dP by dt equals to HFG by TVFG. Then TDS equation. So one is TDS equal to Cp dt minus T V by T at P dP. And there is TDS equal to Cv dt plus T P by T at temperature dV. Then Helmholtz function. H equals to U minus Ts. Then there is a Gibbs function. Gibbs function, which is a correlation between U minus Ts plus PV equal to H minus Ts. Okay. Now we will discuss the revision questions of week 7. Week 7 revision questions. First, comment on the correct correctness of the statement. Whenever a substance expands in a cylinder piston arrangement, the process can be analyzed by the relation PV raised to K equal to constant. So there is such an expression exists, but it is not for all the processes that is happening inside, like that expansion happening inside cylinder piston arrangement. It is only true for polytropic process. Polytropic process or adiabatic process if K equal to gamma. If K equal to gamma equal to Cp by Cv. Okay, this is specific to ideal gas. So substance should be ideal gas. Then adiabatic, reversible, or polytropic process. Not all substance that is getting expanded in a cylinder piston arrangement, you cannot use this correlation. Next is a gas expands in a cylinder piston arrangement from a state 1 to state 2 in an adiabatic reversible manner. In another application, the same expansion is realized in a turbine. Will the specific work output be the same in both cases? The answer is no, not necessarily. Why? Because in cylinder piston arrangement, adiabatic reversible process, if you want to calculate system boundary work, that is like W equal to integral PdV. If it is like truly adiabatic and reversible for the same initial and final state, then the work is change in internal energy, that is U1 minus U2 for an ideal gas, or H1 minus H2 if we are including flow devices. But in a closed system like cylinder piston arrangement, the final velocity of gas can be neglected. So the entire expansion is purely boundary work. Okay. So turbine, if you're saying, usually it is an open system. It is taken as an open system with flow work and some change in kinetic and potential energy. So the device might be operating at a different exit pressure, or it will be having some irreversibility in real practice. But typical turbine have no such boundary displacement like in piston. So they directly convert flow enthalpy into shaft work, right? So when ideal gas is undergoing a reversible adiabatic process from state 1 to state 2, delta U can cause a change in delta H in a steady flow device, because delta U H equal to delta U plus R delta T for an ideal gas. So it is not generally same, but in real turbine, there are additional aspects like flow geometry or possible irreversibility. So we do not expect them to match the cylinder piston expansion work. Okay, so specific work output won't be the same. Answer is no. What are the differences in the processes occurring in a nozzle and a turbine? Nozzle, it is accelerating the fluid from high pressure to low pressure. So it is converting enthalpy into kinetic energy, H to K. And in turbine, what is happening? Turbine, it is extracting shaft work by expanding fluid from high pressure to low pressure. So it is kind of like W shaft equals to M dot H1 minus H2. Okay. So in turbine there is no kinetic energy change, but in nozzle there is a kinetic energy change. Another one is nozzle does not have any shaft work output, but turbine has work output. Then answer the question. I want to accomplish isentropic expansion of superheated steam to a dry saturated state. Should I use a turbine or nozzle or both? So to produce mechanical shaft work, uh, if you are okay with like saturated or slightly wet steam, you can use turbine. Okay, but if you need high velocity flow, and you want an isentropic path from superheated to saturated, you have to use nozzle. So in short, if you want to produce shaft work and you want to expand superheated steam isentropically, it is better to go for turbine. But sometimes nozzles are also used as internal components inside the turbine. So sometimes the turbine has inbuilt nozzles inside them for expansion, and this high velocity jet production and all. But use of turbine is very much necessary for shaft work. Okay, so use a turbine if you need shaft work. If you don't need shaft work but you just need only high velocity jet, what you have to do is go for nozzle. If you specifically want superheated steam to go into a saturated state, then turbine can give that. So I'll say turbine for here. Now, definition of isentropic efficiency of a compressor that we have discussed in the beginning of this lecture. So isentropic efficiency is isentropic work by actual work. Work. Then next is it true? Sorry, which assumption is justified for a pump but not for compressor? For a pump, 1 second. So, okay. For a pump, we assume the working fluid is incompressible. So V is almost constant, or delta V is negligible. Okay, so the work is equal to 0. Like PDV work is 0. Then for a compressor, working fluid is considered to be compressible. Okay, so we cannot assume this delta V equal to 0. So it's about compressibility. For pump, delta V equal to 0. Compressor, delta V not equal to 0. Is it true that when dry saturated vapor is expanded in a turbine or nozzle, the final state will be wet saturated? Dry saturated vapor is expanded in a turbine or nozzle, final state will be wet saturated. That is correct. Because as we expand saturated vapor isentropically, temperature and pressure both will drop. So we are going to get a two-phase region. One is this vapor, another is moisture, water. So if we have this dry saturated vapor and you isentropically expand, then you're moving towards the left side of TS diagram or HS diagram. That is the wet region. Okay. But if you're taking a superheated steam at the inlet, then uh, uh, after this TS, temperature or pressure drop also, you will still be in the superheated regime or dry regime. Okay. So it depends on the initial condition. Here it is written dry saturated vapor. So that means T and P will drop and we will get two phase. Next is dry saturated steam is throttled to a lower pressure. Which of the following are possible final states? One is wet vapor, second is dry saturated vapor, third is superheated vapor. Okay, we have the hint is given constant enthalpy line we have to see. So, if we are thinking about constant enthalpy, in throttling device, what is happening? Throttling device H1 equal to H2. That means enthalpy is going to remain constant. But if our enthalpy H1 is above saturated enthalpy of the final pressure, then we will be having superheated. If initial enthalpy is equal to saturated enthalpy at final pressure, then we will be having dry saturated. And initial enthalpy is less than saturated enthalpy at final pressure, then we will be having wet region. So all these three states are possible depending on the numerical value of enthalpy related to the saturation enthalpy at the throttle pressure. Okay, I'll write it over here. It's a very good question. Okay, I have to write it over here itself. What was the question? Yeah. So does H1 equal to H2? So H2 equal to H sat at P2, then superheated. Then H2 equal to, sorry, H2, um, sorry, my mistake. H2 greater than, right. So initial enthalpy is H1. H1 will be remaining constant. So H2 is also H1. So H1 is above saturated enthalpy of the final pressure. Yeah. So that will be superheated. So H2 greater than H saturated. Then here H2 equal to H saturated at final pressure. Then we will be having dry saturated. And then H2 less than H saturated will be getting wet uh, region 1. Okay. So very important question. Then on a pH diagram, show the condensation of a refrigerant from superheated vapor to subcooled liquid. So you have to draw like superheated region will be right of the saturated vapor line. Then a line will be crossing the two-phase dome, which will be showing condensation from 100% vapor to 100% liquid. Then further cooling below saturation temperature at that pressure into subcooled liquid region. Okay. Then 10th question, liquid carbon dioxide is throttled to ambient pressure. Which of the following could be the final state? 1 second. Somebody joined. Okay. Yeah. So we were saying Um, Liquid carbon dioxide at ambient temperature is throttled to ambient pressure. Which of the following could be the final state? Saturated liquid and saturated vapor, or saturated solid and saturated liquid, or saturated vapor and saturated solid. Uh, so liquid carbon dioxide, uh, it is having a triple point at almost 5 bar and negative 50 degree. So at typical ambient pressure and ambient temperature, that is like 1 bar, which is very very lower than the triple point, and ambient temperature is very very higher than its triple point temperature. CO2 can form dry ice only if temperature drops below the sublimation line. The throttling is like a constant enthalpy process. So depending on the initial enthalpy, final pressure, and the shape of CO2 phase diagram, we are going to cross into a region where some of it can be solid plus vapor, commonly known as the CO2 snow. Okay, so the final mixture typically could be vapor plus solid if final temperature is below the sublimation line. In some cases, we could also have a bit of liquid if we are above the triple point. Hence, it depends on initial condition and how the constant enthalpy line crosses the phase boundary. Often, we will be getting the solid plus vapor mix, or dry ice plus gas. Okay, so the answer will be solid plus vapor. That is the answer. Then isentropic work for a compression process is 5.1 kilowatt. After manufacturing and testing, the power consumed by the pump is 6.2 kilowatt. What is the isentropic efficiency for the compression process? So isentropic efficiency is given by isentropic work by actual work. So that is equal to 5.1 by 6.2. Almost like 80%. Okay, that is the efficiency. Next is a long pipe conveys steam, and near its midpoint there is a drain pipe at the end of which is a steam trap to discharge condensed water. The pipe loses heat to the surrounding, and also the flow experiences pressure drop due to viscous dissipation. Show processes at inlet, outlet, and midpoint on a TS diagram. So inlet to midpoint, steam is cooling, and so steam is cooling means heat is lost, and there will be some pressure drop also because pipe flow, so friction is there. So in TS diagram, the path will be downwards due to cooling, and generally to the left because entropy is also reducing if the heat is being lost. But then if heat loss is there, then along with that friction is also there. So friction is causing some irreversibility. So entropy might be constant also sometimes. So in real practice, we will be seeing a net increase in entropy because friction will be like causing a very large irreversibility in the system. Now at midpoint, what is going to happen is it is saying that some water has condensed and the condensate is drained. Okay, then midpoint to outlet, further heat loss and friction drop will be happening. Okay, so it is going to be like lowering the pressure, like continuous drop in pressure and continuous drop in temperature will be there with a slight increase in entropy. That is going to happen. Now 13th question. Air is being compressed isentropically. in a cylinder piston arrangement. The clearance volume is 1/10 of the swept volume. For one compression stroke and subsequent expansion strokes, sketch the process on a PV diagram. Okay, so compression line from V1 to some intermittent volume. Uh, so that we have to write, show a decrease in V. Then pressure is possibly held near that line pressure. Then the piston, when it gets to the PDC, the valve closes and gas expands back. So we'll be getting a partial compression, then a point where pressure will be constant, and then expansion. Okay. Next is, in the previous problem, an outlet valve opens when the piston has made half the stroke travel. At the end of the stroke, the valve closes and the gas expands until the piston reaches its other extremity. Show these processes in PV diagram. Again, the same kind of question. So it is just equivalent to the previous one. Okay, this question, isentropic efficiencies for steam turbines, pumps, compressor, and nozzle. So steam turbine was around 70 to 90%. Then pumps were around 60 to 80%. Compressor is around 70 to 80%. And nozzles is around 90 to 95%. Now, next question, why is a nozzle used in rocket? So nozzle is used in rocket because we have to accelerate the combustion, the flue gases to a very high velocity. So we'll be getting, because rockets need thrust, right? Thrust is momentum change. Momentum change means velocity change. If there is a high velocity change, then there will be a high momentum change that will give you necessary thrust. So that is why we are using a nozzle. Usually we will be using a CD nozzle because we have to achieve a supersonic exhaust speed. Okay. Now, water at ambient temperature is accelerated in a nozzle until the pressure is about 5 kilopascal. Assuming temperature is constant, what will happen in the flow? So if you truly reduce pressure on liquid water to around 5 kilopascal, the saturation temperature is going to be around 30° plus. That is what is shown in the data. So if water is in ambient temperature, that means we are taking typically room temperature around 25°. Then there will be some cavitation or partial vaporization will be occurring inside the nozzle. So real nozzle cannot maintain pure liquid flow at such a low pressure if the fluid saturation pressure is higher than that. So practically what will happen is bubbles will be forming. Okay, because two phases are going to form due to vapor formation or cavitation. Then insect repellent spray can operated for a minute or so. What do you observe? What is the reason for this observation? What is the propellant in the can and why is it used? Okay, spraying can, what is happening is throttling is happening. Okay, throttling or flash evaporation is happening. So compressed liquid is inside the repellent spray can, and when you are pressing the nose, that uh, whatever is there, that button is there. So if you are pressing that, propellant expands to atmospheric pressure, and when that expansion is happening, partially it will vaporize, and it will absorb the latent heat from the ambient. That causes a cooling effect. Okay, that's also called Joule's effect. So commonly propellants are kind of like CFCs. I don't know what is being used now. Now, what assumptions are made in heat exchanger thermal analysis? Can efficiencies of a heat exchanger be defined? So, heat exchanger typical assumptions are steady state, negligible KEP change, then no external work, and well insulated. From other uh, devices. Heat exchanger, inside that there will be um, the 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 flow, I mean cross flow and all will be there. So one will be coolant, the other will be working fluid. That heat exchange is there. Otherwise, it is like insulated from other devices. Okay, so efficiency is equal to actual heat transfer to maximum possible heat transfer. That is how we define the efficiency of heat exchanger. So that's for today. Thank you. Thank you for attending the session.